So should be this. All right, so we're down to TCP IP. This is essentially a review of the Network Plus course that hopefully you've had. You don't need to know all of the stuff in Net Plus, but you need to know the basics of networking, and it's very important. Oh my goodness, what are this nonsense? Transitions. All right, pardon me. I was doing something else recently. All right, I'm just going to leave it this way. I don't think I'm competent to figure out how to turn off those stinking transitions in a hurry.
You
know where it is?
On the top right. Yep.
Oh, good. Oh, and duration 1 second. Oh, good. How about 0? And is there like apply to all? There doesn't seem to be. Do I have to select them all first somehow?
No, you did.
You think it applied to all? Let's see. That'd be nice. Good. If you people know. Well, I don't know Keynote that well. Oh, nope. That's right. Just did that one. So let's try this. Well, I'm willing to mess around a little bit. Let's try this. Then I can select them all.
Okay.
Then I can change to none.
Okay.
I wonder if that will do it.
That might work.
I don't think I want an effect.
No,
It's not going to work?
No, that's it. That's it. No. You're good.
It's good. Okay, good. That's what I thought. All right, good. I'm glad you people know. I've been struggling with this stuff in various programs. Ah, wonderful. That's what I like. No nonsense. All right, so thank you. I like the tech support. So we're going to talk about TCP IP and a little bit about binary and hex and stuff, which hopefully you already know from previous classes. If you don't know hexadecimal, you got to learn it sooner or later. You're just going to be endlessly humiliated until you learn it. It's like being a musician and not being able to read music. So I've got some stuff from my other classes you can do, although it's not worth credit in this one. I've got some binary games you can play to learn binary and hex. If you haven't, you ought to. Anyway, so TCP IP is a protocol that makes it universal language for all computers to speak. In the beginning, like in the 70s and the 80s when I was doing this stuff, each mainframe manufacturer would just make up their own rules and their own languages, and so you'd have Amdahl's with a big thick pile of manuals and IBM's is a big thick pile of manuals, and they couldn't talk to each other at all because nobody thought of that. Computers cost $1 million and you'd connect everybody to the one computer, and eventually they decided to make the internet and wrote a language called C so they could make this operating system called Unix, and that was going to be the unifying system to make all the computers talk to each other. And that's what it did. And the internet was a Unix invention. And Microsoft came by later and they totally ignored it. Microsoft, their attitude was that the internet is just a waste of time. The only thing that matters is having a local area network with a few computers in a room sharing one printer. That's the only network that anybody should really have. And they totally ignored the internet until Netscape took it over, and then AOL took it over, and then Microsoft jumped in very late and tried to stake some claim at the internet after it became commercially important. But TCP IP is what makes it possible for all kinds of computers to talk to each other without being made by the same manufacturer, and it's just like the electrical standards that come from the IEEE for things like these wall voltages. You can make these plugs, and there's a standard, and if you obey the standard, all these different manufacturers, you don't need to worry which brand of plug you buy to plug in. They're all supposed to do the same thing. And of course, in all parts of it, there are variances in how well people really live up to the standards. And typically, Unix products really obey the standards, and third-party products often don't bother to obey the standards. The worst offender was Microsoft. In addition to deliberately ignoring security, they also deliberately ignored standards. They just didn't care. It was not important to them making money to obey some stupid standard written by Unix people. They would just make Internet Explorer and do anything they want with it and not care because they had 99% of the desktops, and whatever we do, that is the standard. So who cares what a bunch of academics think the standard should be? Anyway, there's the OSI model with 7 layers that you would go through in network class. It is primarily a theoretical model. The reality of how hardware is really built is essentially in the TCP IP model with only 4 layers. The network layer is the physical layer and the network interface. This uses MAC addresses and connects to cables and wireless networks. Then you have the internet layer, which has IP addresses and is used to move data a large distance around the world to find the geographic location of the destination. And once you find the correct computer you're talking to, the transport layer is where you have TCP and UDP ports, which tell the receiving computer which process on that computer you want to talk to. And the application layer is everything above that takes all the data packets that come in and organizes them into something a human can understand, like an image or an email or a video or something up at the human layer. So the application layer is the only thing most users really see. They see a website using HTTP or HTTPS, they see emails they can read, and they press send, and they don't know or care the processes that happen to get that out the wire and over the network to the other person. They just see it at layer 7. Somehow through magic it gets to the other person, they see it at layer 7, and most people just stay there up in the application layer, and they trust us engineers to make sure it works, just like the water in their pipes, and they don't care how it works except when it's broken. So all the protocols that normal people use, like FTP and SSH and IRC, are layer 7 protocols used directly by a human. And so here they are doing the usual things. SNMP is one that may be less familiar if you haven't worked in data centers. SNMP is used to control your network hardware. So you would use SNMP to examine the rules on a firewall. You might use it to find out how much traffic is going through a switch or a router, or how busy a server is. These are all network management commands. Unfortunately, the most popular version of SNMP is a very old version 2, which has no encryption at all. And it does have something called a community string, which is used for authorization, but by default, everyone uses public as the public community string and private as the private community string, which gives you administrator rights. They're typically used in defaults and never changed. And even if you do change it, that's strange. Even if you do change it, it's transmitted in plain text over the wire all the time. So anybody can just sniff it. SNMP version 3 fixes that, but you can't upgrade to it unless all the devices on your network can upgrade to it. And this is what happens all the time. People have some expensive legacy equipment that they're too cheap to upgrade, and they use an old insecure protocol for a long time afterwards. So SNMP is a pretty insecure thing in practice. Anyway, as a matter of fact, I think one of the NSA exploits that was dumped out 10 days ago uses an SNMP packet to take over, I think, Juniper routers, which is not just because it's unencrypted. It also means they have some kind of coding error in the process, like a buffer overflow with the SNMP. All right, so the transport layer, when you have something at layer 7, like say a picture, and you want to email the picture, the picture is too big to fit in an Ethernet frame. Ethernet frames can only carry about 1,500 bytes of data, which is not much at all. So the transport layer cuts your object into chunks of the right size and then labels each one with a TCP packet. TCP is the most common protocol on the internet because it's reliable. What this means is not that it always delivers data the first time it tries. It means it detects whether it got there, and if it didn't get there, it will automatically resend it until it gets there. So if you don't break the connection and wait long enough, TCP will eventually deliver the entire object, the whole email, the whole image. And on top of that, TCP will not bother to sending to people that are not listening. So before you send anything, it does a handshake. This is like the telephone. You say hello, they say hello, whatever you want to say. You don't speak until after that happens because you want to make sure somebody's listening. So they send a SYN, the computer B sends with SYN-ACK back, and you reply with an ACK. There are header fields in the TCP header, SYN, ACK, reset, FIN, and so on. These are just single bit fields that are set. And what this really is two separate handshakes. A SYN, ACK this way to permit transfer that way, and then a SYN, ACK this way to permit transfer the other way. And the intermediate packet is almost always combined into a single packet just for efficiency. The ACK is completing the first pair, and the SYN is starting a second pair. So it typically is a three-way handshake. This is the TCP header format straight from the RFCs. All the internet standards are, in a spirit of humility, labeled request for comment. That's what the IEEE's final product is a request for comment, because they are aware of the fact that nothing is ever finished. Even if you might imagine that something like TCP is perfect, as soon as you put it out, somebody will invent a new gadget or application that needs something else, and there will be some kind of extension or something to it coming out. So everything is in a state of constant revision. But the RFCs are what passes for the Bible of the internet. Reading RFCs is a good thing to do to understand these things. The first few of them you read are very painful to read. It is like reading a chapter of a very dense math book, proving something step by step. They're very tedious. You have to stop in every sentence and Google 3 words. It really is the product of a committee of experts being very, very precise about everything they say. but it's good to get used to it. Anyway, so you have the source port and destination port. These are 16-bit fields, so there are a total of 65,000 possible ports in TCP, and that's all there are. Then you have sequence number and acknowledgement number. Those are 32-bit fields. Those are there to keep track. If you have a 1 megabyte picture and you cut it up into about 600 1.5 kilobyte packets, this will count the bytes. So this packet starts at byte 0, this one starts at byte 1500, this one starts at byte 3000, and on it goes. But instead of starting at 0, the sequence and acknowledgement number now start at a random high value because of the TCP hijacking attack that was popular in the 90s, one of the ones Kevin Mitnick did. He was on the run as a teenager as the most wanted, FBI's most wanted in around 93. He was a teenage computer hacker. He was on the news. He kept the FBI on the run for about 2 years because he was a phreaker and he hacked the phone network and he listened to all the FBI's conversations, so he knew what they were doing and he was always one step ahead of them. He kind of made monkeys of them, and he demonstrated that he was smarter than all the FBI agents. But in the long run, he also demonstrated that being smarter is not enough. I mean, if you irritate the FBI, they don't have to be smarter than you. They have guns and helicopters, and there's more of them, and they'll get you anyway. You might prove you're smart, but it's not going to save you if you bug the FBI. Anyway, so then you come down here. Here's the flags. Here's SYN and ACK, and there's other ones here like push and fin. You terminate a connection with fin. If you finish the transfer in a normal way and you're all done, if you cancel it partway through, like the user got bored and closed the browser instead of finishing, then you send a reset. If you're in China and you're going to a site they don't want you to see, like Google, the Great Firewall of China will send resets on your behalf. So you send a SYN to Google, Google sends a SYN ACK, and the Great Firewall sends reset. Never mind, we decided not to look at that page. Now this, by the way, is a pretty good thing. Now their goal is to stop their citizens from seeing a forbidden site, and it has that effect, but it does not foul up the internet. As far as Google servers are concerned, this happens all the time. Somebody starts making a handshake and they send a reset and give up. That just means, they didn't want to see it. It doesn't cost Google very much. It doesn't flood the network with traffic. If you're going to block something, this is a fairly polite way to do it. It doesn't foul up anybody else. Yeah?
Yeah, I had a similar issue. A friend of mine went to China for a month. They're trying to reach him through Google Mail.
Yeah.
They can't have access to it.
That's right. They can't have Google. Although Google did make Google.cn for a while, where they had a specialty filtered version of Google that would only show the things that the Chinese government liked.
Yes.
But then after China hacked them, Google got very angry, and I think they took it down, but I'm not quite sure the current status of that. By the way, if I can find a piece of paper, I will pass it around to keep a record of who is here. I'll have to use the back of one of these. I keep forgetting to do this. And so I'll put your name on there. I'll try and figure out what day it is later. All right, so, all right, yeah.
What exactly is a host?
A host is anything with an IP address. And therefore, it's a printer, your cell phone. In the early days, they were all servers shared by hundreds of people because they cost $1 million. And that's where I think they got the name host. A host is anything with an IP address now. It's also might as well be called a node, a network node. All right, and so window is actually pretty cool. Window is when you transmit data, you send packets of data, and after a while you send acknowledgments. TCP will wait for an acknowledgement because it wants to know if the data really got there. But you could get an acknowledgement after every packet, and it turns out most of the time, most networks are efficient enough that wastes too much time. TCP is much slower than UDP, and the reason it's slower is because of acknowledgments. I send some data, now I have to wait for the acknowledgement. Now, even if my network is very fast, the speed of light is the limit. So if I'm sending data to like another continent, it's going to take 100 milliseconds to get there and 100 milliseconds to reply. And all that time, I'm sitting here not sending anymore because I don't know if the first data has gotten there. So it takes, each acknowledgement really costs you time. So if you have a reliable network that does not drop packets very often, it doesn't make sense to have an acknowledgement after every packet. You'll change this window size to 8 kilobytes or 16 kilobytes or 32 kilobytes. So it sends a bunch of packets and then gets one acknowledgement for all of them. And that way, you don't spend as much time waiting for acknowledgements. It also means if one of them is dropped, you're going to have to send more packets to replace them, so you find an optimal size for the window. And there are a variety of entertaining attacks where you send packets to a network and you observe the window size, and that tells you if ports are open or closed, even if you can't directly reach them. The window size does tend to leak some information about a network. There are a variety of subtle scanning techniques that use it. but its main thing is to make network transmission more efficient over TCP, which otherwise would be very slow. Microsoft had a huge problem with window size. They used software that I think originally came from IBM, and they chose very poor window sizes, so Windows XP would, if you had a 100 megabit per second network, and you put a file share on a Windows XP machine and moved a file across the network, it would move at 10 megabits per second, only 1/10 of the speed, because it was so inefficient at choosing the window size. It would waste 90% of the time waiting for acknowledgments. They finally fixed it in Vista and Windows 7, and now if you have 100 megabits per second and drag a file, you'll get about 95% of the line speed of real data going through, because they efficiently choose this number. Anyway, so those are the critical things, the TCP flags, the initial sequence number, and the source and destination port. And the thing I didn't finish saying about Kevin Mitnick is if you can predict the sequence numbers, then you can break into someone else's session. Now, a dirty little secret of networking is duplicate packets frequently occur. Various devices get confused and think a packet has been lost and resend it, so it is quite common when I'm waiting for the packet with sequence number 100,000 that I get 2 copies of that packet. So every device is configured, if you get 2 identical packets, to just throw away the second one without notifying anybody because it's just a duplicate. So if I can sneak in my packet with the right sequence number, I can take over a session. So Kevin Mitnick would call up the administrator of a website he doesn't like and say, "Dude, I just hacked your server, ha ha ha." The guy will now log in over FTP to check his files. He waits. Then he'll ping the server and see the sequence number. Then he knows the guy's going to connect and log in. And after he logs in, he sends packets that intercept his packets and take over his session after he's logged in by predicting the sequence number. And the cure for this was to make sequence numbers start out randomly. And all modern operating systems since about Windows 95 have random sequence numbers, so you cannot predict them. So if I make a connection and the administrator makes a connection, there's no relationship between the sequence numbers I get and the sequence numbers the administrator is getting for that reason. Anyway, now you use a different kind of session hijacking. You steal a cookie and replay a cookie and get in someone else's account. That's the modern version of the same thing. So those are the flags, synchronize, acknowledge, push, and so on. The initial sequence number is here. It is there to count the number of bytes that have been transmitted so you can reassemble the data out of all these packets, and if something's dropped, you know what part was dropped, and you just need to resend the packets that were dropped. You don't need to start over and resend the whole thing. So the TCP ports are not physical ports like wires, they are logical ports. They just label data so it can be sorted, and now you can have 65,000 different streams of data coming into your computer, all kept separate. In fact, you can have the square of that, 4 billion, because there's a source port and a destination port in every packet, and each one of those can have 65,000 numbers. So you can have a web server listening on port 80, and you can have 1,000 people using your web server all at once, and they're coming from different IP addresses and source ports. That's how the traffic is sorted. All right, you can block ports on your firewall. If you block all the ports, you might as well cut the cable. No traffic can come in or out. That's no good, which it is best practice to block all the ports you're not using, because, as you're going to be doing in this class, when you take over machines by installing malware on them, one thing you do is you start listening for remote control ports, and if someone uses a firewall, you cannot listen on, like a Metasploit payload by default will listen on port 4444. So if I do install malware on a server and start listening on that port, if they have a firewall, I won't be able to reach it because the firewall will block all traffic on port 4444. You'll only allow traffic through on the ports you're using, and that stops a certain category of attacks. Now, listening processes won't work from off the network. All right, so the well-known ports is a technical term for the first 1,024 ports. And these are the ones that require administrative privileges to listen on, and they're intended for core services that everybody uses, like email and FTP and HTTP and so on. So you need administrator rights to listen on them, and those are the essential services on the internet. You connect to an FTP site through your browser. Port 25 is SMTP to receive email and send email. Port 53 is DNS to resolve alphabetical domain names like cisco.com into IP addresses. Port 69 is for the trivial file transfer protocol. And this had an entertaining denial of service problem. The RFCs said that every packet had to be acknowledged. And if a packet is dropped, you will send an error message, and the error message must be acknowledged, and the acknowledgement to that must be acknowledged. So it works fine until there's an error, and then you have filling the wire with garbage, and it freezes. That's if you actually write the code they told you to write. It was a mistake in the specification. Anyway, they fixed it, but there was a very similar vulnerability in IP version 6. When you have one recommendation from a lot of IP version 6 sources is that you should always use subnets that are /64, which have 16 billion addresses. You should always use that size. And if you have a cable, point-to-point serial cable, you're only using 2 addresses. So you put : : 1 on one end and : 2 on the other end. And you can send a packet to it with a source address of : 3 and a destination address of : 4, and it will go to one end of the cable, and the cable will say, I don't have that address, you better send it to this end. It'll go here and it'll say, I don't have it, you better send it back to this end. It will go bing, 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 back and forth, never getting there, and frees up the cable. It's a similar kind of defect. This tends to happen. Another similar thing is a routing loop, where routers are confused and they send traffic around in a loop instead of getting anywhere. All right, thank you. All right, so port 80 is for HTTP, which is the main port used for the internet. Now we're all moving to port 443, but not too many sites have really done it yet. 110 and 119 are less commonly used protocols. POP3 for an old email client system that not too many people use anymore. 135 is really dangerous. This is remote procedure calls, and the same thing happens when Windows and Unix, they both have this. A remote procedure call is a multi-purpose port where you have an advertising service and you can send a query and say, what services are you providing on this port? And you might be providing 15 or 20 services on that port. You can make all these different requests for service. And the problem with it is typically there are mistakes in that code somewhere. So there's a lot of worms that spread on RPC ports in both Windows and Unix because it offers many services, and that's just more chances that one of them has a buffer overflow or some kind of mistake. That's called an attack surface. The more things you can reach on the server, the more chance that you will find one you can exploit. Anyway, 139 is Microsoft's printer file and printer sharing, which also is the source of an awful lot of exploits. That and port 445 are used for it, and there's just been an endless series of errors in Microsoft's SMB protocol. Many of the famous worms spread through it. 143 is IMAP. So if you make connections to servers, you can see the source and destination port here. If I connect, say, to, maybe I'll do Telnet. Okay, let me just do this, make another window, not that one, this one, all right. And do watch netstat -an, pipe more. Let's see if this works. It does work. All right, that's going to update every 2 seconds and show my network connections. So here is the remote address, or my local address. I'm 147, 144, 202.68. My local address is 63,000 and change. This is connected to something on port 443. That's a secure connection in my browser. So here's the foreign address and port number, the local address and port number, and those 4 numbers are called a socket. That's like a cable. Now data can transmit from my machine to the server and back to me, and it won't be mixed up with anybody else's data. Now it physically goes down the same wire and through the same network card, but it's labeled so it can be sorted at both ends, so I can send a channel of data through that, and all these other channels of data down here will not interfere with it. Yeah?
IP address and port number together is called a socket?
4 numbers. The source and destination IP and the source and destination port number, that's a socket.
Oh, okay.
And the end result is it's as if you now plugged in a cable just for your use. You can now send data both ways without it getting mixed up with any other data. That's the idea. And so if I make a new connection, like I telnet to this server, oh good, it's refusing me. We finally fixed something around here. Let's SSH to it instead. I was hoping. We shouldn't be using telnet anymore. Telnet is evil. But they used to have it at the campus for a very long time. Let's try SSH root at Hills. All right, I'm sure I want to connect. I'll say yes. Okay, now it's asking me for a password, and I don't know it. But the point is, here's my established connection. It's done the SYN/SYNAC ACK, and it has not had a fin or a reset, so that is now an established connection. Here's a listening port that's offering a service to the world. People can send me a SYN, and my computer will answer. And if I quit using something and it times out, I'll hit this closed wait status, and eventually it will tear it down. But see, I now have my established connection on port 22. It's asking me for a password. If I give it junk, it will eventually hang up on me and change that. So that's a socket. If I just cancel it here with Control-C, then my connection to port 22 appears to have vanished right away. So that's the point. That's the way the connections work. All right. You got local and remote ports, and you need them to keep the packets from getting mixed together. You can see them, yeah?
Netstat is the command to see your connections status?
Netstat, yeah, in both Windows and Linux. Yeah, net status shows these. Netstat -A shows all the connections, and netstat -an puts numbers in there. If you don't put the n in, it will actually try to translate it into supposedly helpful things. Let's show you that. I hate this, so I never use it. But if you do netstat -a, pipe more, hey. No, the watch just made it refresh. Let's just do netstat. Netstat. All right. See, instead of 443, it's put HTTPS. That's, the N is what tells it to put numbers there. I would much rather see numbers because, especially if you go to unusual ports, it will put weird letters there I don't recognize because of whatever service it thinks that port is for. Like this, it doesn't know what 1230 is, so it puts it there. But that's what you get if you don't use the N. All right. Anyway, and you can do the same thing in Wireshark. Wireshark is your best friend if you want to learn networking. It's the open source sniffer. Microsoft has a product called Netmon that is vastly inferior and not worth using. So this is showing all the traffic going on my network. Because this is the City College network, it's a flat network. It goes all over the place. If I do a ifconfig of en0 to see my network address, I'm 147.144.202.68, and the broadcast is this address. And I can send, there's two kinds of broadcast address, by the way. This is what's called the directed broadcast, which could in principle be transmitted from off campus, and it would use the first part of that address, 147.144, to move across the world to get here, and then the last part would tell it to send it to every device on the wireless network. Those things don't work anymore, not for decades. They've been turned off on the internet routers because they're used for denial of service attacks. But the other kind of broadcast is the undirected broadcast, and that's this. And if I send to 255.255.255.255, that's a 32-bit address that is all ones, that will send to every device in my local area network. And I get all these answers because that's how many Macintoshes students are using on campus. Windows machines don't answer pings anymore, but Macs do, and the whole Meraki network, or some large part of it, is all spread around. So I'm getting everybody to answer. This is not a good thing, but it does show you how the Smurf attack works. I send out one ping, and I get 100 replies from all those machines, so I can amplify my packets. That's why they don't let you do directed broadcasts anymore, because you can use them to amplify your bandwidth. Anyway, I wanted to show you the TCP handshake. So let's make a connection like that SSH one will do. SSH root at, hey, let's try a root at nsa.gov. They're probably not listening on SSH, are they? Maybe they are. Neat. All right. Let's see. Let's do TCP. You can see all these packets going by. You can filter them here. TCP port equals 22. There we are. So I sent a SYN to the NSA, and I didn't get anywhere, and I tried retransmitting, and I still didn't get there. So the NSA isn't listening. That's kind of comforting. They probably shouldn't be. Wonder if, anyway, let's try Hills. This one's listening. All right. And so I should be able to see the packets that did that, and there they are. So I sent a SYN to port 22, then it sent back a SYN ACK, I sent an ACK. Now we can exchange data, so the server sends me, I send it my client protocol, and it sends back information on server protocol. Then we do a key exchange because this is an encrypted connection. So it sent me a key, I verified, I stored the key, we did a Diffie-Hellman exchange. We'll talk about this in the cryptography section. And after several packets go by to set this up, I can now start sending encrypted data. So let me turn off the sniffing so it quits moving around on me. And so after you do all the key exchange, new keys, and then you can send encrypted data, and it looks like this. I send Ethernet addresses. Let's just collapse some of these foolish things. There we are. Okay, so this is the reality of the TCP model. This is layer 1, 122 bytes. Then layer 2, the Ethernet layer uses MAC addresses. I'm sending from an Apple to a Hewlett-Packard switch. Then I have a Hewlett-Packard server, which is what we're using for Hills. Then I have IP. My source address is here. The destination address is there. They both start 147.144, so I'm not leaving campus. I'm going from one campus location to another. We own the 147.144 Class B, so everything with those addresses is on campus. And if you send anything to City College from off campus, the internet routers only look at the first 2 bytes, 147, 144. That's all they need to know. They deliver it to the campus. The last 2 bytes are our problem locally. The same thing with the post office. All the mail for the college just comes in a big box to one location, and sorting it on campus is our job. All they care about is basically the zip code. And then TCP port, there's the source of port, a random high number, destination port is 22, and here's the data, and the data is just random junk, 804 EAC, that's the encrypted data. Because the previous packets have somehow agreed on a cryptographic key and a cryptographic algorithm, we can now send encrypted data back and forth and nobody can read it unless they have the key, or unless there is some kind of error in the system, and there very often are errors and attacks, and that's why we're here. It's at least encrypted, so you can't just read it, and the general thing about encryption is every couple of years people break encryption and you have to keep updating to the newer version of encryption because people keep finding ways in. All right, so I got a few iClicker questions. If you don't have one, come get one, leave your name behind. If you have something like a business card or a student ID to put in there, that's fine. If you don't have anything expendable, write your name on a scrap of paper. Don't put in driver's licenses or credit cards or anything, because another student might take your ID, and I have no way to control that. And we'll do some of these questions. See if they're fitting on the screen. Looks like they are. All right.
When you say exchange the keys, does it happen automatically without your...
The SSH client does it. So they're running server software, and I'm running client software, and that software does the exchange.
Okay.
And there are protocols for all that. SSH is a standard with an RFC that explains how to do it. And the point of Diffie-Hellman is a system where we can agree on a key without sending the key over the network, where someone could steal it. It's a mathematical system where we scramble things about the key and send some data back and forth that is not equal to the key.
Yes, some under there.
Yeah.
They're not so most important.
That's pretty much it, right?
No, there's another layer. Pull out those and put them over here. Yeah, put it over here, and then we can find room for a whole bunch more.
Oh,
There you go.
oh yeah, that's right. It's flashing now.
There gotta be enough, yeah. Otherwise, it would be seriously unfair, because this is worth extra credit. This is not your test. You don't have to do this, but if you were to get the most right, you get 3 points. Yeah.
So if you had tried to make that connection from your home network to the CCSF network, and you had to find the default gateway, is that just kind of the same way of saying you had to find your router?
Yes. Yeah, the default gateway is just the address that leads off your network. So it's your router, something that can lift the packets off your local network and put them on the internet, the ISP. It's the path to your internet service provider. Now, in complicated mesh networks, it can be more complicated, but in stub networks like your home, where there's only one path out, the default gateway is that address. Yeah?
Is using Wireshark in a public place, like on campus or coffee shop or something, is that legal if you're not doing anything bad with anything you're collecting? Or
That's a very interesting question. It is if you were to find, I would have thought so. Now I'm not so sure, because Google got sued for this. Google sends those Street View cars everywhere, taking pictures, and they're also sniffing the Wi-Fi. Because they want to find all the routers, because they use the Wi-Fi signals to locate you on Google Maps. And then, that wasn't enough for them, they recorded some of the traffic so they could see as they drive by whether it's getting stronger and weaker and stuff, so they recorded some of the packets, and therefore there was a small chance that they might have caught fragments of an email or fragments of someone's password, and they were sued for this as an infringement of someone's privacy, and they pretty much got away with it. I think they paid like 60 grand or something. It was nothing. So it might be a crime, but it's a pretty small crime. This rests on this difficult concept of your expectation of privacy. Like if the cop goes up and looks in your window and sees you smoking pot in there, or yes, pot's legal now, but he sees you doing something illegal in there, unless he has a search warrant, that doesn't count because you had the expectation of privacy. But if you're out on the street doing it, and anybody can see you, then you have no expectation of privacy, and now people can see it. So the question is, if I'm using unencrypted Wi-Fi, sending my data everywhere, do I have an expectation of privacy? And it's gonna be how your lawyer fights the government's lawyer. The fact is, of course, a lot of people are unaware of this, especially on phones and mobile devices. They have no idea whether the data is encrypted or not. Very often apps are doing horrible things with your data and you don't know it. So they say, I thought Facebook was keeping my stuff private. How do I know that Mark Zuckerberg changed the rules and exposed it to the whole world again? Which they just did again last week. WhatsApp. They just decided it's got to connect it to Facebook and leak it to the world. Facebook keeps on doing this. You set up a private account and they say, oh, we decided to share your data with everyone because we can sell more ads. I mean, and because it'll serve you better. It'll serve you better. It'll make you happier. And They even under a Federal Trade Commission ordered to stop doing that, and yet they did it again last week. So then people have probably a pretty good argument saying, I had a reasonable expectation of privacy. When I signed up, the terms of service promised me privacy. Then they shared it with everybody. That's bad. But there's no simple answer to your question. In fact,
but it's relatively safe to do legally.
well, if you don't tell anybody and you don't get caught, then you won't get prosecuted. Now, if you don't use the stolen data to do any harm, it's unlikely that someone will press charges. But that's not the same as it being legal. And this is why, like I say, it's a very shaky thing. And when I went to B-Sides in Las Vegas a few weeks ago, they had a panel with a representative of the Department of Justice there and the EFF and other people. And the guy from the DOJ seriously said, I know the law makes everything you're doing illegal, but you can trust us. We only prosecute the bad guys. We use prosecutorial discretion. It's okay that the law technically means you can't do this. We'll only prosecute you if you're a bad guy. And we're like, well, I don't believe that as much as you want me to believe that. I was hoping for a much more firm foundation for my activity than that. But that's where we're at. I went and took the cell phone sniffing class at B-Sides last year. Now, the guy that wrote Kismet. And you just buy a $30 USB software-defined radio, and you can sniff phone calls in Wireshark. Watch them go by. And he was doing it. I said, holy mackerel. I said, is this legal? He said, oh, yeah, you missed the first day. Everything I'm teaching you is totally illegal. This violates wiretap laws. It's major felonies. You could go down forever. So what you do is you don't tell anybody you're doing it. And you don't send it. I said, well, the problem is I can't go assigning homework like that. I can't have, but the fact is it's technically possible. And you can totally see the phone calls go by and like, holy cow, I didn't know it was that bad. But we can't do it in class or have projects because no. Anyway, that's the way it is. The law is not our friend really in this business. It's a problem. And it's not going to get better anytime soon. Obama wanted to make it more strict to appear tough on crime, tough on cybercrime. He has no interest in letting research get some kind of pass, but he couldn't get that through Congress, thank God. But even if anybody wanted to do something good in the way of cybercrime law, they still couldn't get anything through Congress. So we're stuck with it the way it is for the foreseeable future. Anyway, a very interesting question.
Let's see if they work for us.
What's that?
Let's see if they work for us.
Oh, good idea. Let's make sure everyone knows that. So turn them on at the bottom and make sure you see something. You should be able to choose A through E here. Yeah, good. If you don't have one, come get one. Otherwise, there's no fun at all. Oh, good. How you doing?
I missed the.
Yeah, it's all right.
Okay.
The SFO people didn't come anyway.
Is that right?
Yeah, she called and said she couldn't make it. But anyway, I gave them the link. Turns out those jobs are too advanced anyway.
Yeah. So I'm going to send you my resume so you have it, okay? And
Okay.
because I'm signed up for the class, the repeating.
Oh, sure. But the SFO work will count.
Yeah.
Okay.
Okay,
Good.
great.
Oh,
Thank you.
all
I'm
right.
sending you my resume though, forward.
Sure, that's good
in
to know.
case Gucci calls or
Okay.
Tesla.
I'll let you know. All
Sorry
right.
to interrupt class.
No
It's
problem.
gonna be a great job.
All right, so let's do some of this stuff. So I'll stop this one. Yeah, over on the left they are. But you already got one. It's fine. I see the light from here. What's wrong with it?
Okay.
Yeah. All right. Let's see where. All right. So try this one. All right. All right. So what TCP IP layer has HTTP? All right, 30 will do. All right, that is application. It's, whoa, all over the place. Holy cow. Well, HTTP is websites that humans can see. It's up at the application layer. My goodness. You people may want to review these. All right, so let's see. How about IP? Where's that? All right, looks like I can quit at 30. All right, and that is the internet layer. Ah, you're getting a little better. All right, let's see. All right, How many TCP ports are there? All right. Looks like I can quit at 25. All right, 65,000 and change. 2 to the 16. Good, a popular answer. All right. All right. What TCP port is used for SMTP? Zero? Perhaps it's not listening, huh? Must not be listening. Let me stop it and restart it. Something's not working. Try it now.
No?
It's neat. It was slow to launch. Let's see if I can figure out what the problem is. Something else happening on my machine. Oh, the recording might possibly be draining it, but it didn't in the past. I'm going to clear it and see if restarting this program helps. I can resume the previous session if I'm careful. Yeah, resume session. There we go. Okay, let's see if it is listening now. Try voting. Wow, how rude. I'm going to unplug it. Let's see. All right, one more try. Well, this is going to foul up my beautiful system. Let me see if I can trick it into working. Let's try pulling out the plug. And move it over. That's exactly right. Move it over here. See if it gets any better. Thought I had another USB port over here, but I appear not to. All right, I'll go over to this one again. Let's see if anything good happens. I have another base in my office.
Oh, start session.
If it's the base.
I think you reset it.
Oh, good. Now it's working. Okay. So it just needed to be turned off and on again. That's logical. All right. So I guess I can now quit at 20. Oh, no, wait. Pardon me. You're going to have to do this again. Thank you for telling me. This is going to be mixed up. Oh, crap. Well.
Extra points for everybody.
We'll just have to go from this point. First couple of questions are not going to count then. You got a point. All right. People are getting them wrong anyway, so let's carry on. So, all right. Nothing I can do. My system has gotten too fouled up here. So I'm going to quit at 20, and we will carry on. There's always a few bugs in the system. All right. So that's 25. Good. A popular answer. All right. To be fair, the first two answers appeared to be random anyway. So, how about HTTP? You better know this. Is it listening? Oh, good. All right. All right. I'll quit at 20. I think that's enough. All right. And that's 80, of course. Good, good. All right. So a browser opens this web page. What TCP flags are sent on the first packet? All right, looks like I can quit at 25. All right, the first thing you do is send a SYN to start the handshake. You can't do anything over TCP without first doing SYN, SYNAC, ACK. All right, so let's take a break until 5 after 7, give you about 10 minutes to stretch your legs. I'm going to stop the recording and record the next bit in a different session. It's going 1, 2, 3, chapter 2, A.